right, so let's look at the decile and percentile. Now, the formulas you're seeing here are similar to what you would actually obtain for your quartile. So the formulas are similar to what we got for our quartiles the other time, or what we used to obtain our quartiles the other time. So let's do something about that. So now you, okay, let's copy that, and so we take them, okay, we take the formula, we'll bring the formulas here. So let's see. Okay, so looking at the first quartile, we used 1/4. So you can see the similarity. Just look at that. N plus 1 is similar, but when we're talking about uh, quartiles, we use 4 as the denominator, the divisor here. So 4 here also. And sorry, this is not showing very well. So let me just quickly. All right, so 4 here. So when we are interested in the quartiles, we use 4. That means we have 4 the quartile, your quartiles actually divides your data set into 4 equal parts. So we look at that, and when we are interested in the third quartile, we use 3 here. So when we are interested in the second quartile, we use 2 here. When we are interested in the first quartile, we use 1 here. So we don't need to write that necessarily. We may not necessarily write that. So all right, so we go on, and that's similar for your decile. So for instance, dk, k can be 1 here, and that means you have to put 1 here. It can be 2, and if it is 2, that means you put 2 here. So k can be 9, that's the last value, and that means k will be 9 here. All right, so in a similar way, that's how we obtain, in a similar way, we can obtain the percentiles. And note something, that dk uses 10, meaning that you have 10 deciles, while the percentile uses 100. Oh, sorry, you have 9 deciles actually, but meaning that the decile divides your population, since we're using 10 here, into 10 equal parts, and here, since we're using 100, the percentile divides your data set into 100 equal parts, but we only have 99 percentile. So your percentile divides your data set into 100 equal parts, but we only have 99 percentiles. So whereas your decile divides your population into 10 equal parts, but we only have 9 deciles. So your quartile divides your data set into 4 equal parts, but we only have 3 quartiles. So take note of that. So data set is divided into 10 equal parts in the decile, but we only have 9 deciles. The data set is divided into 100 equal parts using the percentile, but we only have 99 percentiles. The data set is divided into 4 equal parts using the quartile, but we only have 3 quartiles. Now, going to this example, supposing that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 data points. That's 12 observations, and that means n will be, looking at the formula we have here. Okay, I think we have it here already. So you can see dk. So it's in red so that you not be confused as to which one we are considering. So this is the formula, and dk equal to n plus 1 multiplied by k. Okay, we are looking for the 5th percentile, so k is 5, and so that means we are going to say, and n is 12. Don't forget that. So 12 plus 1 multiplied by 5 divided by 10 will give us 6.5. But 6.5 is between 6 and 7. Between 6 and 7. So that means we are interested in the 6th and 7th element. So the 6th element happens to be 4 and the 7th element happens to be 5. So we add them together and divide by 2. That gives us 4.5. So that's what you are seeing here. All right. In that case, okay, since we've gotten what we want, that is we have obtained D5. And D5 happens to be equal to Q2. That's the median. All right, so we go on. We need to obtain, okay, the question is somewhat here. Okay. Okay, the formulas are the ones here. So we need to obtain the 6th percentile, and that will be D6, going by a similar, okay, just in a similar way to what we have done here. We obtain 7.8, and 7.8 happens to be between 7 and 8. So that means we're interested in the 7th and 8th element, and the 7th element happens to be 5, the 7th element, and the 8th element happens to be 5 also. So we add 5 plus 5 divided by 2, that gives us 5. So if you're thinking the 8th element and 7th element, 1, 2, 3, 4, 5, 6, 7, 7th element, and the 8th element is 5. All right, so that's how you obtain that one. We'll go to D9. All right, so the D9, we put 9 here. Okay, so 12 plus 1 times 9 divided by 10, and divided by 10, and that gives us 11.7. And so 11.7 has actually 11.7 is between 11 and 12. So that means we are going to add the 11th and 12th element, and that will give us, and divide that by 2. So the 11th element is 9, the 12th element is 10, and we'll add them and divide by 2. That will give us 9.5. Okay. So 11th element, 12th element. Okay. So 9 plus 10, and we add that and divide by 2. That gives us 9.5. All right, so then okay, so we are done with the first part. So let's go on. All right, this is not actually D. This is percentile actually. So let's copy the question to help us so we can see. Okay. Now, so we can see the question here. So this actually is not D, this is P. Sorry about that. Okay. So this should be P. So P50. And look at the formula again. So the formula for your percentile says PK equal to n plus 1 multiplied by K divided by 100. So please don't forget that. This here. Okay, now that we know that, so P50 will be 12 plus 1 multiplied by 50 divided by 100. So then you get 6.5, and that happens to be what we obtained before for D5. So the element in position 6.5, and that gave us 4.5. So we get the same thing for P50. How do we do that? So just say 4 plus 5. The fifth element is, oh sorry, the sixth element is 4. The seventh element is 5, and you add them and divide by 2. That will give you 4.5. Okay, so we go on. P62. Okay. So this is P62, and P62 equal to all of these. So, and then you get 8.06, and that happens to be between, okay, 8 and 9. 8.06 is between 8 and 9. So as a result of that, we are going to be picking the 8th and ninth element. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the 8th element is 5 and the ninth element is 7. So we add them together and divide by 2, and that will give us 6. So that means 62nd percentile is actually 6. Okay, so the 99th percentile will be 12 plus 1, all in bracket, multiplied by 99 divided by 100, and that actually will be, sorry please, okay, all right, sorry about that. Okay, so now, okay, now we have our 99 percentile to be 12.87. Okay, no, or rather we have our 99 percentile to be in position 12.87. So we cannot have that kind of population. I mean that kind of position, except we consider that that position is between 12, the position 12 and position 13. But don't forget, I mean to say that we are saying that the 99 percentile will be in position 12.87, and that will actually be between, 12 and 13. So, but we don't have a 13th element. Don't forget, we only had 12 observations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that means that our 99 percentile would be the 12th element. And so that means our 99, okay, the 99th percentile will have to be 10. Okay, so that's how you obtain your percentiles and deciles. All right, we're done with that. Now, this also applies to your ungrouped frequency distribution. So you can use this also for your ungrouped frequency distribution. So in a similar way to the one that we did for your quartile. So please take note of that. All right, how do you now obtain deciles and percentiles for group frequency distributions? What you need to do is to understand, if you understood that of the quartile, then you can actually use that knowledge here. You just need to see, okay, don't forget that when we did that of the quartile, for instance, Q2 was L Q2. You may write Q2 here, or you just write median, whichever one. I think I used median the other time, so let me just use median. M, I mean. Okay, so we have 2 divided by 4, n. All right, so you may say 2n divided by 4 is the same thing. So minus f cm. So instead of using m here, I can use q1 if I want to. Then I have f m, or if you like q1. So multiplied by c. Now the only difference, so don't forget what we just finished looking at. Now this one, k, all right, let's do this way. Except for this, just remove this out of the whole thing. Then you have n multiplying k divided by 10. And so that's what you're going to have here. So n multiplied by k, that's k multiplied by n, the same thing, divided by 10. And that is similar to what happened, or what we did for the quartiles. So because we were dividing by 4 when we were doing the quartiles, or when we obtained the formula, or we looked at the formulas for the quartiles, for the deciles, we divide by 10. So we have K because, okay. I think it's very much okay here if I just make this general also. For the quartile, we have a Q subscript K, just have LQ K plus, then you have this to be K N divided by 10, no, divided by 4, since we are doing quartile, minus F C Q K, Q subscript K, all divided by F Q K, F subscript Q subscript K, and that's multiplied by C, where K equal to 1, 2, 3. So this summarizes the formulas for the quartiles: first quartile, second quartile, third quartile. All you need to do is just put 1 in the place of K. Now, so if you look at that and you understand that, we can use that, okay, to the knowledge of that to understand what is happening in the deciles. So the deciles being 9, okay, we have 9 of them. So if you put 1 here, then you have your first decile. So if K is 1, that's your first decile. If K is 2, that's your second decile. And if K is 9, that's your 9th decile. All right, so the way we obtained, so how do you get this? So if for instance, you're interested in the first decile, you need to now say, okay, K multiplied, let's say first decile. So K will be 1. 1 multiplied by N divided by 10. So supposing N is, let's say 6. Okay. Okay, our N, in this case, for instance, this example we have here is 15. So you may just put 15 here. 15. And that should give us 1.5. So where do we have a cumulative frequency of 1.5 for the first time? And that happens to be here. So that means the first decile class is, so is this place. And that means the lower class limit is going to be 0.5. So you put that there. And then what's the frequency of the decile, of the class that contains the first decile? And that is going to be 6. So, and that way you can obtain everything you want to obtain, and it's similar. So if it's similar for all the deciles, so if for instance, we're not interested in the first decile, we are interested in the maybe 7th decile, then I would have had to put 7 here multiplied by 15, and that will give us 105. I believe I'm correct. Okay, so 105 divided by 10. Wait, so we're going to have 105 divided by 10, and that's going to give us 10.5. So I'll now have to come and check where are we going to have 10.5 for the first time in our cumulative frequency, and that happens to be here. So 10.5, I mean a number that is less than or equal to 10.5 for the first time. That happens to be here. And since we have it there, then I can say, okay, this is our 7th decile class. So don't forget, I'm using K equals to 7 here. And so since this is our 7th decile, the class that contains the 7th decile, then we can begin to obtain dk now. That's this 7 in this case. So we can obtain the cumulative frequency before the cumulative frequency of the class that precedes the class containing the 7th decile, and that is going to be, since you said these are the class that contains the 7th decile, so the cumulative frequency of the class preceding the class containing the 7th decile will be 9. So that means this one would have been 9. This will give us 9. Okay. This one will give us 11. This one will give us 11. So how did I get 11? This 11 was obtained from here because it's the frequency of the class containing the 7th decile. And then C is 4. So you can do that for your percentile also using a similar pattern. All you need to do is you are going to be using this one now to determine. So you say K multiplied by N divided by 100, and you use that to determine your the class that your percentile is in. All right, so that being said, we can go on to what we call the Z-score. All right, the Z-score is not a difficult stuff. The Z-score actually uses what you see here. Now, the Z-score, I've written two formulas on the board. The first one is for your population. So don't forget, your population is, maybe you have something like 1,000 students, a population of 1,000 students, for instance. You have 1,000 students, but you don't want to consider all of them in your study, so you may only take 200. If you do that, then you have taken a sample. So your sample will have a size of 200, that's small n, and your population has a size of 1,000, that's capital N. All right, and if you calculate your mean, maybe you obtain the mean using every of the units, every single unit in your population, then you will obtain what we call the population mean. But if you only consider those in your sample and then you obtain the mean, then you have what we call sample mean. All right. Now, in a situation where you obtain the Z-score for your population, then you use this formula. That means you're considering all 1,000 students, or all the 1,000 units. And if you use the sample, then you use this formula. That means you're obtaining the Z-score for only 200 people. So the 200 units. All right, so let's go. The Z-score thing is not difficult. Okay, so this is just to give a summary of your mean, variance, and standard deviation when it has to do with the symbols that you used to represent them, the symbols you used to represent them. Okay, so for the population mean, it's this. For the sample mean, it's this. So like that. All right, so let's move on. What exactly does the Z-score do? The Z-score can be obtained for each and every The Z-score can be obtained for each and every one of the observations in your data set. Actually, the Z-score helps you to normalize your data, or more formally, we may say it helps you to standardize the data set. All right, so what exactly are we saying? Actually, it helps you to make your data in such a form that, like, you're transforming the data to a form that will help you have, to a form that will give us a mean, mean of 0 and a variance of, a variance of 1. Okay. At least approximately, because when you do the z-score thing, you do some approximation. So if you use a sample, then you get this. But if you use your population, then it will be this. So don't get confused about which to use. Usually, somehow you will be told that the data you have is from a population or from a sample. But if you're not told whether it's a population or sample, you can go ahead and use that of the sample. So that's it. All right, so by definition, so we can define it. So by definition, the z-score can be said to be a linear transformation. So a z-score is a linear transformation. The linear transformation of a data point that converts it okay. A z-score is a linear transformation of a data, let me say data set, or given observations. I think I prefer to use that word here. Or okay, let's say data set, such that the transformed data set has a mean of 1 of 0 rather, and variance of 1. All right, now, so since we have a definition for our standard score, let's return back to our example. Let's return back to our example. Okay, now okay. So we can obtain the z-score for each of the observations, or we will be obtaining the z-score for each of the observations in your data. So we'll obtain for 2, for 4, for 3, and like that. So, but before we do that, we need to know our mean, and the mean is this 5.1818, and the standard deviation, which we will obtain from the variance. The variance is actually 5.7638, and that will give us a standard deviation of 2.4008. So how do we obtain the z-scores now? The z1 will be 2 minus mean divided by the standard deviation, and that will give us this. So z2 will be equal to z1. Why? Because z1 is 2 and z2 is also 2. Now z3 will be 3 minus 5.1818. Okay, so divided by the standard deviation again. Mind you, the 3 is not coming because, okay, so understand that if this were to be 8, if we had 8 there, this will still be z3 because what we have here is in position 3. So if this were to be 8, we would have had 8 here, 8 minus the mean divided by the standard deviation. All right, so in continuation, the next number is 4. Do that again. The next number is 4, so Z5 and Z4 have the same Z score because we have 4 to be the observation there. And Z5, okay, Z6 happens to be, okay, the sixth observation happens to be 5, so we will be saying 5 minus the mean divided by the standard deviation. And so the seventh observation, that continues here, 1, 2, 3, 4, 5, 6, 7, 8, 7. Okay, the seventh observation is 6. So this is your data actually. So 6 minus the mean divided by the standard deviation. the eighth observation is 7. So 7 minus the mean divided by the standard deviation. So that's how you get it. So I stopped at Z8 here, but if you continue, you eventually have up to Z11 because there are 11 data points in your data set. All right, so you have them to be what you're seeing here. Okay, now if you take time to add everything that you have here, you will have a mean of 0. And then you will have a variance. If you take the variance, or like if you calculate the variance, you will have 0.9999, something like that, approximately equal to 1. And the mean, if you calculate the mean, it will be 0. So, and that is in line with our definition. The definition that a z-score is a linear transformation of a data set such that the transformed data set has a mean of 0 and a variance of 1. So that's it. And going by that, okay, we actually have a z-score already. So let's do something. Now, for now, don't, I'll come back to why I have this absolute value stuff here. We may want to check for the presence of outliers. And when we want to do that, when we want to check for the presence of outliers, we can use any of these two methods, the z-score. Now, you check the z-score that you have obtained for your data set. If you have anyone, after taking the absolute values, if you have any z-score that is more than 2 or 3, then definitely that observation for which you obtain the z-score, is an outlier. Okay, so let's go back. The absolute value of the first one, Z1, will be 1.3253. So when you take the absolute value of everything, all the negative ones will become positive. The positive ones will remain positive still. All right, so looking at this, when they all become positive, we don't have any observation that is more than 2 or 3. So you may use domain knowledge, or you may decide to keep yours at 2 or keep yours at 3 and say, okay, I want to check if they are greater than 2, or you may decide I want to check if they are greater than 3. Now, but we don't have anyone greater than 2, neither do we have anyone greater than 3. And in that case, it means we don't have an outlier in the data set. Now, let's take the second method. Let's look at the second method rather. Now, interquartile range. So the interquartile range method, what do? We obtain we obtain an interval, so a lower bound and then an upper bound, such that if any observation falls outside the bound, it may fall outside the boundary or the limit. It may fall outside this interval, maybe to the left or to the right. So if it falls to the left or to the right, but doesn't fall inside this interval, then definitely that observation will be said to be an outlier. For example, look at this the data set we have here. Now, when the Q1 is 2, the Q3 is 6. Now we can obtain the interquartile range to be 6 minus 2. That will give us 4. And then when we calculate the lower bound, we have it to be minus 4. So you just substitute your your interquartile range, which you have gotten from here, to be 4. Here, multiply it by 1.5, and then you move the product from 2, and that will give you minus 4. If you multiply 1.5, please don't forget the formula, by the interquartile range again, you get 6. But this time around, you add it to the third quartile, which we obtained earlier, and that is 6. So don't forget, you can see that here. and that will give us, so 6 plus 6, that will be 12. All right, so now looking at the interval, we have minus 4, 12. So we don't have any observation that is lower than minus 4. Neither do we have any observation that is higher than 12. So definitely we have no outlier. But supposing we had maybe minus 5 here, or even minus 4 point, even 1, that observation is going to be an outlier. So if we had maybe 13 or even 12.5, that observation is going to be an outlier. So because it falls outside this boundary. So what I'm saying is 4 less than or equal to, so let's assume 12. So if whatever you put here anyway, so our boundary, we are looking for the x's that are not in this interval here. So if it is not in the interval, so any x that is in this interval is not an outlier. But once the x does not meet this condition, I mean the particular observation does not meet this condition, it becomes an outlier. All right, so those are the ways by which you can check. Okay, these are the ways. So your z-score and your interquartile range are the ways by which you can check for the presence of outliers. So with that, we have come to the end of this. We have come to the end of this lesson. Thank you.